Faraday's law of electrolysis is named after Michael Faraday, a British scientist. And, I don't know, is it even worth trying to list everything that Michael Faraday contributed to science?
No, there is too much. Let me sum up.
So here's a guy that begins his career by inventing the Bunsen burner, discovers benzene. He's talking about diamagnetism and electrical fields way before anybody else was even taking them seriously. I even had to call this video Faraday's Law of Electrolysis because just saying Faraday's Law isn't specific enough. There are still more than one Faraday's Law in use in science. The Faraday's Law that we want to talk about today stems from the correlation he noticed between the amount of current that was flowing through a circuit and the change in the mass of an electrode when it was held in a solution of metal ions. The change in mass would be greater if the current was applied for a longer period or if the amperage was raised. The ampere measures how much charge is moving past a point per second. And so charge, measured in coulombs, is equal to amperes multiplied by seconds. Increasing either the amperage or the time increases the charge. Now bear in mind, this was still decades before the electron would be discovered, or that Avogadro's number was established. Now people then were talking about the equivalent volumes of gases, and were leaning towards the idea of a molar amount, but even the existence of atoms hadn't really been confirmed, let alone the existence of ions, or the oxidation state of atoms. So it's a bit historically inaccurate to say that Faraday determined the amount of charge on a mole of electrons by comparing the moles of atoms that could be reduced from a solution of ions. But that's what he did. Even today, we can't directly monitor the transfer of electrons from reactant to product. Fortunately for us, Faraday's constant gives us a conversion factor that we can use to compare charge to the moles of electrons. Remember that charge is the product of current and time. So when we couple this to a balanced redox reaction, we can use the moles of electrons stoichiometrically to find the moles of atoms oxidized or reduced over a given amount of time if we know the amperage, or what the current must be if we already know the time. This is how Faraday framed the relationship and how it's still used in electroplating. The Oscar statues, for instance, undergo several layers of electroplating in copper, nickel, silver, and finally gold. Gold isn't easy to get into aqueous solution in the first place. If we didn't know the oxidation state of aqueous gold, we could use Faraday's constant and a known oxidation state of a different metal to determine the oxidation state of gold. Suppose that a quantity of electric charge deposits 0.732 grams of silver from an aqueous solution of silver nitrate onto the Oscar statue. When that same quantity of charge is passed through a solution of gold salt, 0.446 grams of gold metal forms on the statuette. So what is the oxidation state of the gold, and how long would we need to apply a current of 15 amps to apply exactly 0.500 grams of gold? We start by looking at the balanced reduction reaction of silver, or one silver ion plus an electron is converted into a silver metal atom. So because the silver ion has an oxidation state of +1, we need to add 1 mole of electrons to achieve 1 mole of silver deposited onto the statue. We can find the moles of electrons needed to convert the silver by determining how many moles of silver actually plated onto the statue. That's 0.732 grams times 1 mole per 107.87 grams, the molar mass of silver, times 1 mole of electrons per mole of silver, telling us that 6.79 times 10 to the negative 3 moles of electrons were transferred through the circuit into the statue. And from the question, we know that that's also as many electrons as we needed to plate 0.446 grams of gold. That's 0.466 grams times 1 mole per 196.97 grams, or 2.26 times 10 to the negative 3 moles of gold. So it took 6.79 times 10 to the negative 3 moles of electrons to reduce 2.26 times 10 to the negative 3 moles of gold ions onto the metal. 3 electrons per gold ion, meaning that the balanced reduction equation must be gold 3 plus 3 electrons convert into the gold metal atom. And the oxidation state of the gold in solution was +3. So knowing that, how long would it take to plate exactly half a gram of gold onto the statuettes? That's 0.500 grams times 1 mole per 196.97 grams, or 2.538 times 10 to the negative 3 moles of gold. We multiply that by 3 moles of electrons per mole of gold to find that we need 7.615 times 10 to the negative 3 moles of electrons to plate out exactly half a gram of gold. To convert from moles of electrons to time in the bath at 15 amps, we need to use Faraday's law. So 7.615 times 10 to the negative 3 moles of electrons times 96,485 coulombs per mole of electron gives us 734.77 coulombs of charge. Now coulombs are amps times second. So at 15 amps, it would take 48.98 seconds exactly. If we round up to 49 seconds, it would only add an extra 0.0002 grams of gold. And with gold sitting at $68.92 per gram, that would increase the dollar value of each statue by around 1.5 cents. But that's not likely the values that their owners care about.